Okay, guys, we can now move on to section 3.9, which is all about derivatives of exponential and logarithmic. Didn't leave enough room. Try that again. Exponential and logarithmic functions. All right, so first things first is let's figure out what the derivative of e to the x is. Derivative of e to the x. So if I did this the long way, what I would do is I would do the limit as h approaches 0 of e to the x plus h minus e all over h, right? We learned this in section 3.1 or 2, I'm not sure which one, but this is how we did this the long way, right? Well, if I look up here, we have e to the x plus h, right? Well, using our power rules for exponents, we can rewrite that. Since we are adding them, we can write that as e to the x times e to the h minus e to the x all over h. Well, if we look, both of these terms on top right there have e to the x. So we can factor that out. E to the x times e to the h minus 1 all over an h. But because I'm wanting this as h approaches 0, and this e to the x does not have an h there, I can actually bring that out front. E to the x times the limit as h goes to 0. Again, because there's no h there, and so I can just pull that out. And then we have e to the h minus 1 over h. So we have not learned yet how to do this, but what I can do is I can draw the graph of it and then see what that is, right? So if we graph e to the h minus 1 over h, we get this graph right here. And if I let the h get really close to 0, I can see my y gets really close to 1, right? If you look right there. You can zoom in if it helps. It gets really close to a 1 right there. Therefore, this part right here is equal to 1. So that's e to the x times 1. Look at that. That is e to the x. So this really cool fact that I have now is that the derivative of e to the x is simply e to the x. So what I'm trying to say here is e stays e. And that's why we really like e in all math, is because e stays e. There's no change there. So we can use this fact to find the derivatives of some more complicated stuff. Example. Again, e stays e. Example. Let's find the derivative of e to the power of 3x plus 8. E to the power of 3x plus 8. So first things first is I can tell straight up I'm going to need the chain rule, because I don't just have e to the x, I have e raised to a bunch of stuff, right? So because of that, I need to use the chain rule, right? So the outside most part is the e, because it's e raised to some stuff. So I'm going to start with the e. As we just saw, e stays e. So we're going to start with just e to the power of 3x plus 8. But now, because of the chain rule, I have to find the derivative of that stuff up here, right? The derivative of 3x plus 8 is just 3. So multiply that by 3. If you want to, you could just stop right there, and that's fine. Or if you would rather write it as 3 e to the power of 3x plus 8, that's okay too. It doesn't matter at all. Again, we get the e part because e stays e, but by the chain rule, I have to also find the derivative of that stuff. So that's why I've got to do e times 3. Another example. let's find the derivative of x times e to the 2x. For this one, I'm going to need the product rule because this is a product. I have x times e, right? So therefore, I need the product rule. By that rule, we're going to take the derivative of the first part. The derivative of x is a 1, so that's just 1 times e to the 2x, plus leave the first part, so just x, and then do that part. Again, I have e raised to some stuff. We know e stays e, so it's going to start with just e to the 2x. But by the chain rule, I have to now do the derivative of that stuff. The derivative of 2x is just 2. So multiply this by 2. Again, we can leave it just like this, and that's completely fine. Or if you would prefer, you can write this as e to the 2x plus 2x e to the 2x. Either way, it doesn't matter. Another example. Let's do the derivative of e to the power of tangent 2x. Again, here we are going to need the chain rule because it's e raised to some stuff, right? So again, the outermost part is the e because it's e raised to all of this. E stays e, so we're going to start with e to the power of tangent 2x. Again, because e stays e, it's just going to stay what it was to start with. But now, because it's e raised to some stuff, I have to find the derivative of that stuff. The derivative of tangent is secant squared. So times secant squared of 2x. But I still can't stop because this is tangent of 2x. And so now I've got to do 2x. The derivative of 2x is 2. So multiply that by 2. So this one had 3 parts, and so I used the chain rule twice. Because first we had e stays e, and then we had tangent, that becomes secant squared, and then we had 2x, and that is now 2. One more example, using e. The derivative of e to the x squared over an x. So this is a quotient, and therefore we need the quotient rule, right? Remember that's low d high, high d low. So we're going to start with low, which means I'm just going to leave the denominator. D high, which means I'm going to do the derivative of the top part. Remember, e stays e, so e to the x squared, but I've got to use the chain rule. The derivative of x squared is 2x. And then minus high d low. So high means I'm going to leave the numerator times the derivative of the denominator, which would just be a 1. So times a 1, which I don't even have to put there, right? All of that over the denominator squared, so that's x squared. Again, you can just leave it just like this, and that's okay. If you want to try to simplify this, you would have 2x times x, so 2x squared times e to the x squared minus e to the x squared over x squared. But again, you don't have to, and that's okay. You just leave it. However, all right, so we've done e. Now let's look at the natural log. Okay. So now we're going to find the derivative of the natural log. So remember, if I let y be equal to the natural log of x, this is e, because this is base e. E, again, a logarithm tells you what the power is, so it's e to the power of y is equal to x. And the reason I might want to rewrite this like this is because I know how to find the derivative of an e. So I can use that to find what the derivative of the natural log is. Okay. So now I can take the derivative of all of this. So first start over here. Remember we said e stays e, so that's just going to be e to the y. But like we said, whenever I take the derivative of a y term, I have to multiply that by dy dx is equal to, and then the derivative of x is just a 1. So now I can solve this for dy dx by dividing by e to the y to cancel it out. So I know the derivative is equal to 1 over e to the y. But like we said in this step right here, e to the y is equal to x. So I can write this as the derivative is equal to 1 over, like I just said, that is x. Therefore, I have this fact now. The derivative of the natural log of x is just 1 over x, which is really helpful. Again, the derivative of ln of x is just 1 over x. So, as an example, let me kind of separate this. As an example, let's find the derivative of the natural log of x cubed plus 3x minus 4. So we know that whenever it's just ln of an x, I get 1 over x, right? So I'm going to start this the same way. 1 over what's inside of here. So x cubed plus 3x minus 4. But since this is ln of a bunch of stuff, I've got to use the chain rule. And so now I find the derivative of this stuff now. The derivative of x cubed plus 3x minus 4 is 3x squared plus 3. So again, you can leave it just like this, and that is okay. A lot of people like to write this as 3x squared plus 3 over x cubed plus 3x minus 4, and that is fine too. It doesn't matter how you write these out. Let me get another board for the next example. Let's find the derivative of the natural log of 3x plus 2 to the 5th. So I want to make a note about the notation here. Okay? I'm going to pause really quick because I think the recording stopped. Let me check on it. Oh, there it goes. It did not stop. Okay, so sorry. I will keep on then. Okay. Okay, yeah, I wanted to make a note about how this is written out. Okay, so if there was a bracket around this like that, if there was a bracket right here, what this would mean is I'm taking this entire thing right here raised to the 5th. Okay, but the brackets aren't there. So whenever it's written in this way, what it actually means is I'm taking the natural log of all of that stuff, okay? So the 5 is inside of here with the 3x plus 2. So this is the natural log of 3x plus 2 raised to the 5th. Okay, I just want to make that clear. And the reason we need to make sure that's clear is because when I use the chain rule, I need to know what the outermost part is. For this case, it's the logarithm. Okay, so again, by the chain rule, I do the logarithm part to start with. We know that's 1 over all the stuff, so 1 over 3x plus 2 to the 5th. But now I have to do the derivative of that stuff. So since I have a bunch of stuff raised to the 5th, I use the power rule to bring my 5 down. So times 5 times, leave all this stuff, and my new power would then be minus 1, and you get a 4. But again, by the chain rule, now I have to find the derivative of this stuff. Okay, the derivative of 3x plus 2 is 3. So again, you can leave it just like this, and that's okay. Or if you want to, you can rewrite this. 5 times 3 is equal to 15. And I would have 3x plus 2 to the 4th on top over 3x plus 2 to the 5th on the bottom. And if you notice here, I have 4 of them up here, 5 of them here, so I can cancel 4 of them out. And I'm left with just 15 over 3x plus 2. And that'll work. Let's do another example with the natural log. Let's do... You know what, I'm actually going to get a different board for this one because there's a lot I want to say about it. Derivative of the natural log of x squared sine of x over 2x plus 1. So the reason I said there's a lot I want to say about that one is because there are actually several ways to do this, okay? The first way is how I have been, right? So I know the derivative of a logarithm is 1 over the stuff, right? Well, 1 over a fraction means I'm just going to flip it, right? So whenever I do 1 over all of this stuff, that's just going to flip it. So now it's going to be 2x plus 1 over x squared sine of x. But now I have to find the derivative of the stuff, right? So that's where I'm going to use the quotient rule because this is a quotient. So it's low d high, high d low, right? So low means the denominator stays, 2x plus 1. D high means I'm going to do the derivative of the top part. This is a product, and so I need the product rule, which states I'm going to do the first part. The derivative of x squared is 2x. Leave the second part. Plus, leave the first part, so x squared, times the derivative of this part, which would be cosine of x. Minus high d low. So high means we're going to leave the numerator and then take the derivative of the denominator. So the derivative of 2x plus 1 is 2. All of that over the denominator squared. So 2x plus 1 squared. Here it is. Now, as you can tell, that was a huge mess, right? And it's easy to kind of get lost here, right? Another way to do this is, remember, we have all the log rules, right? All of our log rules. Hang on, I'm just rewriting it to keep everything straight. Remember our log rules from pre-cal or some other class, right? If I have log of a product, I can split it up by doing log of A plus log of B. If I have log of a quotient, I can subtract them, so log of A minus log of B. And then if I have a power in there, so like log of A to the R, I can bring my power down to the front and write that as R log of A. So the reason I said no those is because I can actually separate this so that it's not so bad of a term, right? Because this is a mess, as we saw here, right? So instead, I can actually split this up and instead take the derivative of, I see right here, I have the product of x squared sine x, so I can use this first rule and add those. But also, because it's x squared, I can bring my 2 down to the front, right? So I can write this as 2 ln of x plus the ln of sine of x. Again, because this is a product, and so I can do ln of x squared plus ln of sine. But because it's x squared, I can bring my 2 down. So 2 ln x came from the x squared, and then ln of sine of x. And then I'm dividing that by 2x plus 1. So then using this rule right here, I can subtract ln of 2x plus 1. Now the reason I might want to do this is because Remember, I have 2, so I can just leave that as a 2. The derivative of ln of x, we already said, was 1 over x. So this term, that's done. Moving on over here. ln means I do 1 over that stuff, so 1 over sine of x, times the derivative of the stuff. The derivative of sine is cosine. And then minus ln of some stuff, so that's 1 over the stuff, times the derivative of that stuff. The derivative of 2x plus 1 is just 2. That was not as much work as what I did here, right? But they are both the same thing. If we were to simplify these, you would get the same thing. So what we have seen so far is if I have e raised to some stuff, and then if I have log base e, right? But what happens if my bases are not e, right? That's what I want to look at now. What if my bases are not e? So let's start by wanting to do y equals log base b of x. Well, remember from like pre-calculus or whatever class you took before Cal 1, I can rewrite log base b of x as the ln of x divided by the ln of that b. This is called the change of base formula. So if I wanted to find the derivative of this, then y prime is the derivative of ln of x over ln of that b, right? Well, ln of b is going to be a constant because I'm going to know what the base is. So ln of b is a constant, which means I can bring it out front, times the derivative of ln of x, which we already know. We know that is 1 over x. So the derivative would be 1 over that x, because of this, times ln of b. So my point here is that the derivative of log base b of x is equal to 1 over x ln of b. Now I can use this rule to find the derivative of another base to the power of x. So a base other than e. It's going to be a known one though, okay? So since I have y equals b to the x, I can write that as a logarithm as log base b of y is equal to x, right? So I can take the derivative of this now using what I have here, okay? So log base b of a y, I know I'm going to get 1 over y ln of b, but since it's in terms of a y, I have to multiply that by dy dx is equal to the derivative of an x is equal to 1. So solving this for dy dx, I can multiply both sides by y ln of b to cancel it out. So I get dy dx is equal to y ln of b. But like we said right here, y is equal to b to the x. So the derivative is b to the x times ln of b. So the moral of this is that the derivative of b to the power of x is b to the x times ln of b. So these are two new rules I have if my base is not an e, which most times it won't be, right? E is just really nice because it isn't hard because e stays e. But like we said right here, it will not always be e. Alright, so let's do some examples when my base is not e, using these two new rules. Example. Let's find the derivative of 2 to the x. Okay. Well, this is just a base raised to the x, which is this rule we just did. And as we saw, what I'm going to get then is the same base raised to x times the natural log of that base. So all that this is the base raised to x times the natural log of that base. That's it. Easy enough. Another example. Let's find the derivative of cosine of x times 4 to the x. Now notice here I said times, so this is a product, and therefore I need the product rule, okay? Remember that says, do the first part. The derivative of cosine is negative sine. Leave that part, so leave 4 to the x. Plus, leave the first part, so cosine of x is going to stay, times the derivative of this part. So we have a base to the x, so we leave it as 4 to the x, but we need to multiply it by the natural log of that base. So here we go. Again, we got this part using our new rule here. Another example. Let's find the derivative of log base 3 of x. Again, we have a rule for that now. Remember, whenever I have log base b, it's just 1 over x times the natural log of that b, right? So for this case, again, it's a logarithm, so we know we're starting with 1 over x. But since my base is not equal to e, I have to times it by the natural log of that base. And that's it. Another example. Let's do the derivative of log base 4 of the sine of 2x. Okay, so this is a logarithm, so I know it's going to be 1 over the stuff. So 1 over sine of 2x, but since my base is not equal to e, I've got to also times that by the natural log of my base, so natural log of 4. But since this is log of a bunch of stuff, I've got to use the chain rule and find the derivative of the stuff. Okay, so the derivative of sine is cosine, so cosine of 2x. But again, this is sine of some stuff, and so now I've got to do that stuff. The derivative of 2x is 2. So multiply that by 2. Here it is. So on all of these, I can use every rule I already know, like the product rule, quotient rule, power rule, chain rule, all of those, just with these new rules I have now, these new ones here. So there's actually something really cool I can do using this. Okay, so using all of this stuff, there's actually something I can do that's really cool. Sorry, I'm getting all my notes straight. Example. Let's find the derivative of x to the x. So looking at this straight up, your first thought might be, okay, let's use the power rule, right? But the power rule only works if my power is a known constant, right? So like if I had like x squared, I could do that. Or if I had like x to the 9th or that kind of thing, where I know what the power is. But here, my power is an x, so I cannot use the power rule. Then your thought might be, well, I can just use this new rule I just had right here, right? I can do that. But the problem with that is with this rule, I know what the base is. So I would have like 2 to the x, 8 to the x, right? On this one, neither one of them are known. So it doesn't really help us a whole lot. So what I'm going to do instead is I'm going to rewrite this as y equals x to the x. And let's think this through, okay? Again, the reason I'm kind of stuck is because I don't know what the power is. So it would be extremely helpful if I didn't have a power here. That would help us a lot. So let's think about this. Is there any math concept I can use where I can get rid of a power? Okay. Well, we said whenever I have a power inside of a logarithm, I can bring my power down to the front, right? So if x to the x was inside of a logarithm, I could do that. So why don't we take the natural log on both sides? So the natural log of y equals the natural log of x to the x. Now the reason this is helpful is because now since there's a now that there's a power inside of a logarithm, I can bring my power down to the front, right? That's that logarithm rule that I wrote down up here. I hope it didn't get too smudged. If I have a power in there, I can bring it out to the front, right? I'm doing exactly that. So I'm going to rewrite this, bring my x down. Natural log of y equals x times ln of x. I still have not done any calculus here, right? I'm just trying to find a way to rewrite this so that I can bring my power down. And I did so by taking the natural log on both sides. Okay. So now that I have it right here, I can use the product rule. And so that's helpful. So now I can take the derivative of this using the power rule. So on the left side here, ln of a y, we know that that'll just be 1 over y. But since it's a y, I have to multiply that by dy dx. And then over here, I'm going to use the product rule because it's x times ln of x. So do the first part and I get a 1. So that's 1 times, leave that part, ln of x, plus, leave the first part as just an x, times the derivative of that part, which is 1 over x. Well, what's really nice is I have x times 1 over x, and so that's just a 1. So 1 over y dy dx equals ln of x. Again, that's plus a 1. But I'm solving for dy dx, so multiply both sides by the y to get rid of this y here. So I get dy dx is equal to ln of x plus 1 times a y. But if you look back to up here, I already know what the y is. So I can replace this in there in place of the y. So the derivative is equal to ln of x plus 1 times y, which we said was x to the x. So my point here is that if it's in a form where I'm kind of stuck, I can take the natural log of both sides and bring my power down to the front, and it'll help me out. Okay. Again, if you want to, you can rewrite this as x to the x ln of x plus x to the x. Doesn't matter though, just stopping here is fine. Alright, let's do another example of this. The derivative of 2x to the 4th plus 1 to the power of tangent x. Again, here, just looking at this, it can't be done because I don't know for sure what the base or what the power is. So therefore, there's not a rule here I can do. So instead, let's rewrite it as y equals 2x to the 4th plus 1 to the power of tangent of x. And to hopefully bring my power down to the front to help me out, I'm going to take the natural log of both sides there. And the reason that is a helpful thing is because now I have a power inside of a logarithm, so I can bring my power down front. Again, that's not a calculus thing, that's just how the logarithms work, right? So tangent of x, let's put parentheses around there to help me out, times the natural log of 2x to the 4th plus 1. So now that I have it turned into a product, I can use the product rule. Taking the derivative of the left side here, ln of y becomes 1 over y, but since it's a y, we have to put dy dx equals, this is a product, and so then I'm going to use the product rule. Do the first part. The derivative of tangent is secant squared. leave that part, so leave ln of 2x to the fourth plus 1, plus leave the first part, tangent of x, times the derivative of that part. Well, that'll be 1 over the 2x to the fourth plus 1, but then I need to multiply that by the derivative of this stuff. The derivative of 2x to the fourth plus a 1 would be 8x to the third. So I would say times 8x to the third. So to solve this for dy dx, we would need to multiply by y to cancel it out. Multiply all of this by y. So you get dy dx equals secant squared of x times the natural log of 2x to the fourth plus 1 plus tangent of x. Let's rewrite this by putting the 8x to the third on top. But again, it doesn't matter. You don't have to. Times y. But we already know what the y is. We said up here y is equal to 2x to the fourth plus 1 to the power of tangent x. So there it is. Again, we wanted our power down to the front so that I could use the product rule. And so I've got to put it inside of a logarithm. So that's exactly what we did there. Let's do one more example of this. Let's find the derivative of x times the square root of 2x plus 1 over e to the x sine cubed of x. Now this one we could actually do this using the quotient rule. However, that would be a mess. And so we can do the same thing for this one. Okay, we can do the same thing. We can rewrite this as y equals x to the square root of 2x plus 1 over e to the x sine cubed of x. And I can rewrite this with the log rules to help us out. So I can take the natural log on both sides. And just like the example we did a while ago, we can break this up, right? So I can have ln of y equals everything on top I can write as ln of x plus, this is a square root, and a square root is like having a power of 1/2. And like we have said a bunch of times, I can bring my power down to the front, so plus 1/2 ln of 2x plus 1. Again, because it's a square root, so the power is 1/2. I am dividing all of this stuff, so that's minus ln of e to the x. Remember that ln is log base e. So this is log base e of e. They cancel out, and that's just x. So e to the x becomes just an x. And then minus, this is the natural log of sine cubed. So I can bring my 3 out to the front. 3 natural log of sine x. So now I can take the derivative of this instead of this monstrous thing here. Okay, so the natural log of y becomes 1 over y, but because it's a y, we have to multiply it by dy dx equals the derivative of ln of x is 1 over x plus 1/2, and then ln becomes 1 over that stuff, so 1 over 2x plus 1 times the derivative of that stuff. The derivative of 2x plus 1 is 2, so times 2. The derivative of x is a 1, so minus 1. And then minus 3. Whenever I do a logarithm, it's 1 over that stuff times the derivative of that stuff. So now I just have to multiply everything by y. Everything by y, and for dy dx you get 1 over x. Notice here I have 1/2 times 2, they cancel out, so plus 1 over 2x plus 1 minus 1 minus 3 cosine of x over sine of x. All of that times the y, but I know y is equal to x square roots of 2x plus 1 over e to the x sine cubed of x. So again, this is just a way to do this without having to do the quotient rule, because it would have been a mess, because it's the whole low d high d low thing, and so I would need like product rules and power rules and all kinds of stuff. Whereas with this, I don't need all of that stuff. Okay. This process here is called logarithmic differentiation. And that is when I take the log before I take the derivative. And that's a very neat trick and tool I now have.